My name is Charlotte Dryden. I work at Intel Corporation where I lead a visual computing solutions team. So I'm moderating the Tech Insights Track 2 sessions today. Our next speaker is Praveen Nayak from PathPartner. He's a tech lead there, and he's speaking with us about using deep learning for video event detection on a compute budget.
All right, my name is Praveen Nayak. I'm a technical lead at PathPartner Technology, and today I'm going to be talking about using deep learning for video event detection on a compute budget. So the presentation, I've structured it in this way. I'm going to be talking about what video event detection is, firstly. I'm going to be talking about what it takes to work with video data. Then I'm going to move on to learning representations from video, as in how can we use deep learning methods to leverage the redundancies in video data and learn compact representations. And then I'm going to be talking about moving from video representations to video event detection. And finally, our proposed method to have some kind of trade-off between the representational complexity and the computational complexity, and a case study that we have done on a publicly available data set. So let me just get started. So basically, for any machine learning or signal processing algorithm, video data is basically a 3D signal. Just like an image is a 2D signal, video data is a 3D signal that is limited by, that you can traverse across using your spatial coordinates and your temporal coordinates. So we are working with two modalities, actually, the spatial and the temporal modality. And one way to interpret videos is as a sequence of frames. So we fix the time index and we obtain a frame. So one way that we can understand videos is as a sequence of frames. And the notion of sampling in a video volume works pretty much the same way as it does in images. So there's sampling in both space and time direction that's possible to do because this is just any other 3D digital signal. And event detection is basically the task of retrieving the start and end times of an event of interest. So that event could be based on the task that we are interested in. If it's a surveillance application, it could be, if it's a sports, a very good example is the previous, presentation that we had. If it's things like surveillance or things like, sport detection or, detecting the start and end times of certain events in a video that has sport in it. So basically, we use this general term called event detection, and it involves getting the start and end time of that event. So for instance, in this example, if we have a basketball dunk happening, so the task is to get the start and end time of that basketball dunk. So we're not really interested in where the event is happening in the 2D window that we have in the frame. We are more interested in when it is happening, right? So that is basically the event detection notion that I'm talking about. So let me just get started with. Now we know that video is a 3D signal. Basically, how do we go about learning efficient representations from video? So the first effort in this direction was, as again presented in the previous presentation, was spatio-temporal fusion networks. So this involves operating on the spatial and temporal modality separately using two-stream networks. So you have one stream that operates purely on the visual domain and one stream that operates on the motion information. That could be optical flow of some sort. So basically, this is kind of a complex architecture in the sense that there are two different streams that are operating on the same data. And the input to the second stream, which is the motion stream, also requires some additional computation of optical flow from the video. So the question arose, is it possible to learn a kind of joint space-time representation rather than two-stream kind of representation? And C3D is one of them that was published by Facebook, I believe, in 2014 or so. So basically, this C3D is pretty much like the VGG of the video world. And yeah, basically every single convolution in C3D is spatio-temporal convolution. And you have striding not just in space, but also in time. So all your volumes are 5-dimensional tensors, technically. And We are able to learn joint appearance and motion features at every layer. We don't really need to feed a separate optical flow stream of some sort and do a fusion at a later stage. So this is some kind of a slow fusion technique, to learn joint appearance and motion features throughout the length of the network. And the state-of-the-art video descriptors right now look something like this. You can see that they are some combination of two-stream and 3D convolutions. So the best performing networks right now try to employ these two paradigms to construct a network that can do a bit of both. Sort of leverage the best parts of both the ideas. And typically the data sets that are used to evaluate, the standard data sets that are used to evaluate these kind of algorithms are UCF 101, HMDB, and Kinetics. Kinetics is relatively recent. It was just published by DeepMind, I believe, last year, a couple of years back. And for basically the video classification task, we are more interested in one decision per clip. We are not yet into the domain of event detection. I'll get into that soon. So the metric for these kind of tasks, for the event inference task, or rather the video inference task, is similar to MS COCO or ImageNet like metrics. It's basically the mean average precision, and the classifier it has to just make one decision per clip. So. Basically, these are some of the publicly available results on the data sets that we're talking about. Like I said, the state-of-the-art descriptors mostly employ 3D convolutions and two-stream fusion of some sort. So now that we know what exists in the sense of extracting meaningful representations from video using deep learning, how do we construct an event detector from this, right? And the solution is more straightforward than you think, I would say. So basically, people the initial pieces of literature in this domain drew parallels mostly from object detection. So we already have something called RCNN that does object detection in 2D. This was basically just extended into 3D. They just called it a segment CNN network. And the meta-architecture used can be pretty much anything that was in the previous slide. But for the sake of the slides here, I'm just presenting it as C3D. So you could use C3D features to pretty much any event detector module. So basically, in the segment CNN approach, similar to RCNN, it involves three parts, essentially. So it involves a multi-scale segment generation. So you generate segments of different scales and different temporal persistence. And each sort of segment is evaluated independently by a C3D-like module, which, needless to say, is very, very, very computationally intensive, because the number of segments you can generate in that time direction is a huge number, actually. It need not necessarily be confined to an image. Like an image is confined to something like 255 by 255, and you need to if you are striding across it, you would have a finite number of steps that you need to go. But an event can be of arbitrary length, right? So you can have events of 30 frames, you can have events of 512, or even longer, maybe even 5 minutes long. And generating segments of that length can be really, really computationally expensive for the inference module to evaluate. So the other sort of approach in this direction was to draw parallels from what actually improved the speed in RCNN-like frameworks, which was basically drawing parallels from faster RCNN. So they split the problem into two parts. One was the class-sensitive proposal generation, followed by the inference. And this whole sequence is end-to-end trainable thanks to the SOI pooling, which is exactly the same as ROI pooling in faster RCNN. So this, again, is a pretty good idea in the sense that we are generating segment proposals before actually evaluating them. But the issue with this, again, is that the base meta-architecture of C3D needs to run for every single frame, right? Which makes this a really complex thing to do anyway, because something like C3D, which is something like 24 gigamax per frame or per volume, needs to run for every single frame in the video. So this is what the landscape looks like in terms of the computational cost versus the accuracy or the MAP in terms of event detectors that exist. So I just spoke about C3D, SCNN, and TALNet. TALNet is Temporal Action Localization Net. And basically, the relationship here between the table here basically shows the gigamax per video. I'm coining that right now because I'm saying that we need to be running that detector for that many number of frames. So you can see that gigamax per inference and gigamax per video are just related linearly by the number of frames. So gigamax per inference times the number of frames is literally gigamax per video. So the total number of max that I need to process the entire video is basically the gigamax per inference times the number of frames. So in this scenario, you can see that something like SCNN, the segment CNN, which is the second column, or the second row, I'm sorry, consumes something like 237K gigamax for a video of 3,000 frames, right? Which is quite a lot. So basically, in all these, right, the complexity stems from the fact that we have to run that base meta architecture of C3D for every single frame. So the question we try to ask is it even necessary to run C3D for every single frame? Is it possible to get a somewhat low complexity segment proposals that can call C3D on demand? So which is exactly what we try to do. We try to decouple the when from the what, right? So like I said, we are breaking down the problem into two parts. One is the class agnostic segment proposal, which we have designed it to be a sort of low complexity model, and the video segment inference model, which can be something like C3D that depends on the nature of the video and the task. So the inference model that we are using to finally say what event it is may be short-term or long-term temporal. It could have LSTMs or whatever in it. But the key thing here is that we can call it on demand based on the low complexity model. And the characteristics of a good segment proposal, in my view, is that it needs to cater to arbitrary event lengths, discriminate event from background, because we're talking about class agnostic event detection. So essentially what we're doing is we're splitting the problem into two parts. The event detection part involves distinguishing between different events and the background. We're just using a segment proposal to distinguish between background and event irrespective of what the event is, and using the inference model to say what exactly the event is. So the segment proposal basically just distinguishes between the background and any event. It doesn't care about what event it is. So that allowed us to actually reduce the complexity quite a bit. So how does one build such a class agnostic segment proposal model? So one way of doing this, in our view, is to formulate the problem as an anomaly detection, right? So we train a model to learn the anomalies against the background, and at deployment, we are basically predicting a binary label, that is whether an anomaly has occurred or not. And one way of training an anomaly detector is pretty much the oldest trick in the book, which is autoencoder. But this is a kind of different autoencoder in the sense that we are learning how to represent video. So we are trying to learn the characteristics of a background so that we can distinguish it from any event. So a video autoencoder framework has two parts essentially. It has an encoder and decoder, and the encoder and decoder are pretty much mirror images of each other. But both the encoder and the decoder need to operate on the space and time modality, because this is video that we are talking about. So we are using a low complexity 2D, a couple of layers of a CNN as the convolutional encoder for translating the information from the image domain to something in a latent representation space. And we're using a Conv-LSTM, which basically retains the spatial structure along with learning temporal characteristics. And the task of this video autoencoder is to learn a sparse low-dimensional encoding for whatever input sequences we pass to it. And basically, it's trained end-to-end using L2 loss, and the job of the decoder is to provide the supervision signal such that we get a high fidelity or high quality reconstruction. What is key here in the context of an anomaly detector is we want to learn to represent the background, right? So that at deployment time, when the event occurs, the reconstruction error is poor. So we are basing the anomaly decision based on something called a regularity score, which we are extracting from the error itself, the L2 error. So we are basically just rescaling the L2 error between the Rmax and Rmin, which is derived. This is basically the minimum and maximum errors, which are derived on a validation set, a deployment ready set, let's say. And we have found that an anomaly detector of this kind, we are able to represent background events in a data set like UCF101 at about 0.8 gigamax per frame. So this is not really a complex model, and we have experimentally found that we are able to represent backgrounds quite effectively using a model as simple as this. So overall, the event detection pipeline looks something like this. We have the middle graph is basically the output of the anomaly detector, which is giving us outputs of the regularity score. We just threshold the regularity score to say whether an event has happened or not. And quite obviously, that threshold value is something that's key here. Choosing the threshold value is something that's key here. And basically, based on the threshold value, we decide whether or not to call the C3D or the high complexity inference model. So, like I said, it's the key in the anomaly detector right now turns out to be the choice of the threshold, and basically this is again experimentally obtained for extremely large values of the threshold R. You may end up with a lot of false detections. For smaller values of R, you may end up missing events altogether. So there is a computational trade-off here, basically. So if you're allowing for a lot of event proposals, you would end up with a very large computational requirement at the cost. The benefit you would be getting at that point is you would be getting a greater recall, right? So the trade-off between the computational requirements and the accuracy is pretty much controlled by this threshold right now, because of the way we are structuring the event detection system. So these are some of the results that we obtained on the Thumos 15 subset of the UCF101 dataset. In the UCF101 dataset, it's got 101 events of human activities, among which we are only using the 20 which have these event labels. So this was a part of CVPR 15 Thumos challenge. And you can see from the first table on the top that as we are increasing the threshold, our recall improves, so does the number of frame proposals that we have, but it comes at the cost of reduction in average precision. So basically the number of false positives increases. And in comparison to the other methods which do something similar in terms of region proposals, we are able to get pretty large gains in terms of gigamax per video. So it's almost it's almost 1/6 that of temporal action localization net, which requires C3D for every single frame. So the other interesting thing about this is, we just looked at what exactly the segment proposals are doing. So this is basically the confusion matrix that we have of those 20 events. And you can see that the confusion between the events, it's diagonal major, so basically the recall, the diagonal talks about the recall, the performance of the model in terms of recall. But in terms of the false positives we have, it's quite distributed across different events. So there's a high chance that you may be confusing one event with another. But with the segment proposals that we have, we are basically introducing another trade-off, which is with respect to the event and the background. So we have a module that is filtering out a bunch of events, so it's reducing the confusion between the events, but that comes at the cost of increased confusion between the event and the background. So this is what the overall landscape looks like now. In this graph, the black diamond shows the performance of our model versus the rest of the literature. So basically the comparison point is against TALNet again, which is the temporal action localization net, against which we are almost able to retain the same amount of accuracy, but we're able to reduce the number of gigamax by about a factor of 6. It's 1/6 almost. So to summarize, the event detection in video is with joint temporal spatiotemporal features is kind of computationally intensive, and decoupling, doing the kind of decoupling that we are doing, that is, having a class agnostic segment proposal and an event inference module separately, gives you a good gives you a control over the trade-off between accuracy and computational complexity. And this also comes with an added advantage. You also have, a logical point of separation in the event detection algorithm. So on systems which have the capability of multiple processing units, you can run the a region proposal module, the segment proposal module, at a much higher rate on a low-powered part or low-powered compute part of the embedded system. So it enables a much effective heterogeneous compute. And like I've already mentioned, the accuracy complexity trade-off is controlled by the quality of the segment proposals and the choice of parameters of the segment proposal. So yeah, that's about it from my side.
All right. Thank you very much.
Yeah, sure.
Does anyone have any questions?
What kind of hardware are you actually running this on? Try.
Right. So we've been running this on NVIDIA platforms, NVIDIA TX2 platforms, and Xavier. But right now, I don't really have the numbers in terms of time. I just have the numbers in terms of gigamax saved. Yeah. So we have seen that a lot of it translates to time, in the sense that lowering the number of gigamax by changing the algorithm itself can give you gains in time as well, quite clearly.
Okay. Thank you very much. Nice job.
Thank you so much.